All right, any other questions? All right, I believe we last left with the bent wire. And then someone dared say we were out of time. All right. Bent wire is conducting. And then over top of it, we lay another wire. This is a movable wire. I'm not sure if it's supposed to be movable or not, but it's there. And of course, no problem like this would be complete without a external magnetic field. So let's have external magnetic field coming out of the board. All right, so what is the current flowing through the wire? And in which direction?
Which part? Or which wire?
The movable wire.
Movable wire.
No. How'd you get up?
Wait, so magnetic field going that
Okay.
way,
Or
or that way?
yeah, it's going, magnetic field's going that way.
Oh, okay. No.
Would not go up.
You go left?
The current in the movable wire go left, and it goes to that side of the wire.
Is that 4 times? Well, if it doesn't go up,
Let's go down.
then does it go down?
No.
Does it not have a current?
Yeah, there we go. There's no reason for there to be a current. So let's flash back then. It was an easy question. Faraday-Lentz's law is equal to the spot on. The negative change in the magnetic flux with respect to time. The textbook does have a capital N in front of it. And the capital N is indicating that that's if you have multiple loops. And so just so you are aware, I usually don't write the capital N here and just sort of built that into the flux itself. Textbook tends to do the flux of one loop times the number of loops. So, but we have only one loop here, only one layer. So we need a change in the magnetic flux. And so if it's not moving the magnetic field, if it's uniform, the area is uniform, there's no change in the flux. However, if the wire moves out at some speed v, now what is the direction of the current in the movable wire? And again, up or down? You just taking a 50-50 shot, or are you feeling good with that? Both? Okay. So let's go 75%?
Yeah.
Confident? All right. Anyone with a greater confidence in an answer?
Chester is.
So what does this minus sign indicate?
Oh,
What?
it's like the direction, right? Does that mean the like?
It means it's always gonna go in the direction to reduce the flux.
Close. It's not always going to reduce the flux.
A change in flux.
Yes, it's always going to reduce the change in flux. So if the flux is getting bigger, it's going to try to reduce the change. It's going to try to make it smaller. If the flux is getting smaller, it's going to try to make it bigger. So as the wire comes out this way, is the flux increasing or decreasing?
Increase.
Why?
It's creating more area.
Yes. Magnetic flux is V dot A. All right, so our area is getting bigger. So if I want to, let's also flash back to, if I have a wire here with a current flowing this way, what is the direction of the magnetic field that is induced inside? If I have a current flowing, it's counterclockwise, what is the direction of the magnetic field inside the loop here?
Out of the board.
Why?
Some minutes.
Okay. Anna, why?
Right angle? Well,
Yeah. So how would you, so you can do it two ways. One, you can put your thumb in the direction of the current flow. And so it's going into the board on top, out of the board there, or in, out. Every way I put my hand in the direction of the current, thumb in the direction of the current, that the magnetic field is coming out and then into the board here. Or it also turns out, using that logic, if I curl my fingers in the direction of the current flow, my thumb points in the direction of the magnetic field, as well as the magnetic dipole moment. So, if I want to reduce the magnetic field, I want to create a magnetic field that opposes that one. Sorry, if I want to reduce the magnetic flux, or the increase in the magnetic flux, then I want my magnetic field to go into the board from this, therefore current has to flow that way. So, someone's going to challenge me on that? That way.
I didn't think it made sense.
That's feeling better. Because I want the current to flow clockwise so that the magnetic field it produces goes into the board. Bless you. All right, we are going to now derive what I refer to as the Princess Bride equation.
Wait.
Who has not seen The Princess Bride? It is a requirement by the end of the semester, you have seen The Princess Bride. I did this in one class and I said, you need to watch it, I'm gonna require it, and then I did extra credit questions at the very end on The Princess Bride. Not necessarily gonna do that this semester, I may or may not, but you really need to see it. If you ever watch Honest trailers, he tends to hate every film.
Yeah.
He starts on The Princess Bride and then stops and says, no, I can't even criticize this one.
Yes.
Wait, so the direction you down, right? Or you up?
So in this case, it would be, yes, it would be down through the movable wire.
Right.
All right, so I know that the voltage here that is induced is going to be equal to the negative change in this. I'm going to ignore the negative sign. Like a lot of the stuff we do in this class, we can just think through which the direction is and not worry about the minus sign in terms of the calculation. And so all I'm going to do is just look at the change in the magnetic flux with time. And magnetic flux, V dot A. So I have the change in V dot A. Now, in my scenario, I have my magnetic field. Actually, what is the direction of my area vector?
This way, that way.
Yes. Because this is my area right here. Area vector is perpendicular to it. So my magnetic field and area vector are perpendicular, or either parallel or anti-parallel, depending on how you want to set it up. You know, all that, if it's anti-parallel, that means we're throwing an extra minus sign. It doesn't change the overall direction. So this is just the change in BA. If you want to throw an extra minus sign in there, have at it, but ultimately I'm ignoring it. My magnetic field is not changing, so I'm just going to pull that out. What is the area?
Well, it's not a constant, it's changing.
Okay, how would you find it?
You'd have to probably find the speed at which the movable wire is moving.
The speed is speed.
Okay. Then you go from there, I don't know where to start.
I mean, we don't have any, like, lengths or anything.
All right, so why don't we make this lengths and what else do you need?
The width, which is what's changing.
And that'll show up here. All right, so my area is length times width, so I have B times the change in length times width over time. My length is not changing, so it just comes out. So this is BL, change in width, it's supposed to be a W, not an omega, over change in time. And what is the change in the width over time?
Speed.
Yeah. So the voltage that is created by having this wire move, and granted we do have constant speed and constant length and a constant magnetic field, is BLEV, thus the Prince's Bride reference. Because don't forget what Billy Crystal heard when they pumped air into Wesley. He said to BLEV. His wife heard true love, but you know, we all know it was a physics reference. I don't think I spoiled anything on that one. All right, questions to hear before we actually use some numbers and something? Just use numbers. By the way, we could have looked at this slightly differently. Instead of doing it from Faraday-Lentz's law point of view, if instead we had looked at which way are the electrons forced in this wire here, or which way would protons be forced, even though the protons aren't going to move. Which way is current going to flow in this wire as it moves in the magnetic field? Well, if I think about, I got protons moving in that direction. My magnetic field is coming out. So therefore, the force on the positive charges is down. Therefore, electrons will be forced upwards, which is opposite of the direction of the current. So current flows down. You can do it from that point of view as well. They do match. So let's say this is copper wire. This is 5 meters. This is, let's make it 15 meters, 20 meters. This is going to move at 10 meters per second. The magnetic field, let's make it huge, 7 Tesla. Oh, copper wire, number 28, copper wire. what is the current in the wire? So the bent wire and the movable wire are all copper wire, number 28. Ooh. I suppose I have a copy of the lab here so that we can control that. Oh, here. All right, good. All right, so first thing we need to do, figure out what is the voltage that's pushing the charge. Well, that straight like a jug. So the EMF is equal to 7 Tesla times 15 meters times 10 meters per second.
What did you say about voltage?
This is the EMF, this is the voltage.
Oh,
So an ideal voltage.
$10.50.
1050?
Meter squared per second and Tesla.
And then throw a Tesla in at the end?
Yeah.
Okay, so Tesla meter squared per second?
I'm not sure what you mean. I mean.
You said meter squared per second, then times Tesla.
Yeah, so it's that right there.
Yeah, I just threw the Tesla in front.
First.
What is this? So there's a one-word version of this.
Did you already tell us?
Did I already tell you? No. I mean,
Well, it is also a Weber per second. Because a Weber is a Tesla meter squared.
okay.
I don't know what the one you haven't told us yet is though.
is that a Weber?
Weber. The unit of magnetic flux. But there's still a one word.
Would you care to enlighten us if we don't know it yet?
We actually used this word for a month and a half now.
Is it Fahrenheit? Not Fahrenheit.
Yep.
Volts? Is it?
Yes,
Yeah.
it's a voltage. Better be a volt.
So Weber per second is also a volt.
Apparently. So if a Weber per second is equal to a volt, then we have a new unit of time, the second being the Weber per volt. Fun with units. Who doesn't love fun with units? All right, so we haven't answered the question yet. The question is, what is the current flowing through the wire? So we have a voltage now. Now what?
You use voltage to find the current.
Use what?
Voltage to find the current.
All right, sounds like a plan. How do we do that?
Good question. Oh.
Current equals resistance over changing voltage. So if we find the resistance.
Current is resistance over changing voltage. Don't buy that.
My notes say.
Yeah, you got something a little off there.
It's voltage over resistance.
Yeah, voltage over resistance.
Oh.
Ohm's law, delta V equals IR, therefore I is equal to delta V over R. You know the voltage part, but we don't know the resistance. What is the resistance?
The resistance is
That R equals rho times area over, or no, rho times length over area.
There we go. All right, so resistance, rho L over A. Rho, that's why I was making sure I had this information here. 1.68 times 10 to the negative 8th of meters. Number 28, copper. I do have the calculation right here. 8.04247 times 10 to the negative 8th square meters. Times the length. What is the length?
15 meters.
Current's flowing in more than just that one wire.
well, you're gonna have 30 meters from the 15 and the 15, and then
Yeah, so,
And what do we end up with the resistance being?
that's 7.3.
Here?
Yeah.
That's 7.7.
Okay.
I'm just double, yeah, 7.7.
8.04247. I got 14.622. Ohms.
All right. So we now can find the current, because we had a huge voltage there, 1,050 volts divided by 14.622 ohms. It's less than 100. It's 70-ish. Seventy-one, 72.
So 81.81.
Have you?
And the excitement doing this. All right, questions to hear?
That says 71.8, and, or is that an extra one?
That's an extra one. Let's see here. All right. So now, theater of the mind. Suppose I have a metal bar here, and I drop it. Now, I don't have a complete circuit, but I am going to have charges moving. So if I have a bar here and I just drop it, which way will the charges move? So I guess we need to figure out the direction of the magnetic field, and I guess north is that way. So let's pretend the magnetic field lines are running that way, so let me drop the bar, hold the bar east-west, and I let go. Which way will the charges be forced?
You said What's pointing?
Magnetic field going that way.
Down.
Uh,
What are the options?
I don't wanna do that.
east, west, north, south, up, down. When I say forced also, I mean, I'm not referring to, forced by the force of gravity. So, that way?
Yes.
I saw 2 people using the right hand rule, 3 people. It is a right hand rule thing. So, if it's falling, what is the direction that we're sending the charges? We're shooting the charges in which direction? Yes, down. Which direction is the magnetic field? So, the positive charges are going to be forced towards the board, the negative charges will be forced towards the window. What's actually going to move?
The electrons.
Okay, what's the direction of the current? Towards the board. So, we can still use this equation right here, because we have a magnetic field, we have a length of the wire or rod or whatever it happens to be, and then we have a certain speed to it. So as it falls, well, the speed's going to increase. And as the speed increases, well, we have a greater voltage. And that's going to, so we should be getting the current increasing until it hits the ground, and then V drops down to 0. Unlike over here, as this wire moves off to the right at a constant speed, my voltage will stay the same as long as V is constant. However, as I increase the amount of wire that the current has to run through, I am increasing resistance, and so current should drop as that thing moves off to the right. So we have a way of creating a magnetic field from current. We now have a way of creating current from magnetic field. Questions to hear?
Sorry about that, but I'm just saying, like, where would we use this example, like in real life?
Where would you? Or
Where
where
would-
would,
how-
how is this
yeah.
mankind use it?
Yeah, as mankind uses bent wire, conducting, movable wire. Just starlight, something like that.
All right, so we basically, at this point, have changed the magnetic, we had a constant magnetic field, and what we've done is, here we changed the area, and thus changing the magnetic flux. I could also change the magnetic field, and also induce a current, or, as it's more commonly used in the world, remember that flux is the magnetic field dot A. What does the dot product tell you?
The amount of one vector in the direction of the other vector.
Okay, so is there a metal loop somewhere around in this room?
There's just a bunch of rocks.
Yeah. All right, let me grab a prop at least. All right, the prop. And no, you will not see me doing it. Even if I tried, you would not see me doing it. All right, so I have imagine that this is a metal wire, and I got a magnetic field going that way. So, direction of my area vector, since it's an open surface, it's either that way or that way. We'll just choose that way. All right, so if my area is, I'll just say 1 square meter, and my magnetic field is 2 Tesla, what's the flux?
Two,
2 what?
buckets? You know,
Yeah, okay.
or
What's the flux now?
0.
Magnetic field's going that way. My area vector's that way. The dot product.
Oh,
My area vector and my magnetic field are perpendicular to each other. The dot product is 0. So it starts out at 2, 0.
-2. 0. 2.
All right. So all I've done here is just move my wire and I've changed the flux. If I've changed the flux, what's going to happen?
You change the EMF.
Okay, and therefore,
The voltage.
you changed the magnetic field.
You create a current.
that's what I was going for right there. All right, so basically by taking this through a magnetic field, I have created a current in this wire. So, did I say that right? Just in case I didn't. So just by rotating this thing around, I'm changing the magnetic flux through it, and therefore I'm creating a voltage, and therefore I'm creating current. That is the essence of power generation throughout the entire world. You create a magnetic, you can either do one of two things. You either have a fixed wire right here and you rotate the magnet around it, or you have a fixed magnet and you rotate the wire around, the wire through it. And that's, now, so if I've got the north and south ends of a magnet here, so of course my magnetic field's going this way, and then I've got a loop in it. Now, as this loop is spinning around, these two are connected to, I think it's called the coupler. How it's connected to the coupler affects whether it's AC or DC. That since basically I'm going to have current flowing through the hoop one way, then it drops to 0, then it flows to the other